Yet another video on looking at resin structures, because it cannot be emphasized enough your ability to be able to predict these types of things. So here we have phenol, and phenol is benzene with an OH group. In this case, we've extracted the hydrogen. So why is this structure stabilized? Why is it more stable to form this O- than you'd expect? So let's look at it in terms of a resin structure. Now, we've only got one set of lone pairs here, so let's start with that on the oxygen. If we take one of these lone pairs, we can convert it to a double bond between the oxygen and the carbon. So let's look at that first resin structure. Now, this should make you feel very uncomfortable for multiple reasons, based on where I've stopped it. So first of all, we have a carbon with 5 bonds around it. We know we can't have that. The second is that we know that if we have this type of angle, it's going to be really unstable for double bonds that are attachment to each other, right beside each other. So what we're going to do, we're going to take this double bond and we're going to break it. And we're going to put our negative charge on this particular carbon. So one way to stabilize this O- anion is to take this double bond, single bond, make it to a double bond, and break this double bond, move the negative charge to here. What else can we do? Well, we can take this lone pair, create a double bond, again, this should be another one that makes you feel very uncomfortable. Put the negative charge on that carbon. Well, again, for the same reason we didn't like it up here, we don't like it here. We've got carbon with 5 bonds around it. There's a hydrogen that's not being shown in the structure. So what we can do is we can break the double bond. Again, we've conserved the number of electrons in the structure and we're just moving the charge around the molecule. So, does this make sense? Well, yeah, it kind of does. I mean, carbon here has 8 electrons around its coordination sphere. We can do the same thing again. We can take this lone pair, form a double bond, and again, this should make you feel very uncomfortable because we've got carbon with 5 bonds, 2 to this carbon, 2 to this carbon, 1 to the hydrogen. So we're going to break it and put our lone pairs there. Now, what could we do with this structure? Well, we could reconnect the double bond. Once again, we're in the same situation we were before when we started with this resin structure to here. We're going to need to break this oxygen carbon double bond, put our negative charge back on. So, what did we do here? Well, one resin structure is to make a double bond and break another one, put the negative charge here. Another solution is to move this double bond, put a negative charge here, put a negative charge here, and this effectively recovers our starting structure. But if for whatever reason we had a fluorine here or some reason that would create asymmetry in the molecule, you'd see that it's a different resin structure than the parent compound. In this case, they just happen to be the same by symmetry. So we have 1, 2, 3, 4, 5 different resin structures we can draw in terms of this molecule. So this is how we can stabilize this molecule through resonance. And our reasoning here was to say, let's take a lone pair, let's make a double bond between it and the nearest atom. And if possible, let's move that if we have too many bonds around the atoms we're going to, in this case carbon, let's just create a negative charge on whatever's beside. We'll make one double bond by breaking another one. Now, this will also explain the reactivity of this molecule, because what this resin structures are predicting is that there is a situation where this can act like an anion with this being the source of the negative charge. So when it acts like a Lewis base, we're going to form a bond using these lone pairs. But it also explains how we could form a bond here, and a bond here. Now notice that in none of the stable drawings, so we did show ones where we've got 5 bonds around this carbon, none of the stable pictures do we have a negative charge here or here. It either is there, or there. So what we don't predict based on these resin structures is any reactivities where we'd have a reaction at this position or this position, which is what we see experimentally. So this is how you can draw the different resin structures for this particular molecule.